David Anthony joining us today. He's a senior research engineer in the Perception Systems section at Southwest Research Institute. His research interests include robotics, unmanned aerial systems, machine learning, and wireless sensor networks. At SWIRI, he has led research efforts into exploring damaged nuclear power plants with small UAS, applying machine learning to factory automation systems, and localization techniques for off-road vehicles. He has received his PhD in computer engineering from University of Nebraska in 2016, where his focus was on using UAS and wireless sensor networks for environmental monitoring. This is going to be a great talk for all of us who are thinking about how to deploy machine learning in the real world. What are the constraints we need to think about? And specifically for students in the AI practicum course, this might be a great seminar to think more about your upcoming projects. Without further ado, David, the floor is yours.
All right, thank you very much for that kind introduction. Yes, my name is David Anthony. I'm over here at Southwest Research. And today I'm going to be talking about some of our experiences moving kind of machine learning from laboratory settings to true deployments. So a little bit of background on myself, if I can get my cursor going, is as previously mentioned, I'm from Nebraska, did all my degrees there. Started off doing did my bachelor's in computer and electrical engineering. I went into the industrial world and worked at Garmin International doing marine software engineering, so they're boating hardware or software. And then after a while, I decided I wanted to tackle some more kind of academic problems. So I went back to school, got my master's in computer science, and then did my PhD in computer engineering. And I've been at SWIRI ever since. And kind of the common theme behind all of my kind of work and career interests is I'm very interested in practical things and kind of moving and doing real field work. So on the right is some pictures from my master's and PhD. My master's, I was deploying wireless sensor networks to these sandhill cranes you can see we've got in the picture on the bottom left. And then when I moved to robotics, I started doing a lot of work with agronomists and the agriculture world. So really SWIRI was a good fit for me because we do applied research here. So this is kind of our stock slide showing how we operate here at SWIRI. If you're not familiar with us, we're not really a university. We don't typically do a lot of fundamental science, but we're also not building products like I was in industry. So we're bridging this valley of death, which is where a lot of good ideas fail to transition to the real world, which makes our talk today really interesting because machine learning and AI is such a hot topic in academia that I think it's interesting seeing how we are successfully deploying it in industry and how we are kind of failing sometimes. This is also SWIRI. We like to say we do everything from deep sea to deep space. So we've built the pressure hull for the Alvin submersible. And then now our space science division does probes like New Horizons and Lucy. New Horizons is now somewhere out in the Kuiper Belt beyond Pluto. Lucy is a mission that recently launched that's going to go explore satellites. And we do everything in between. We do any type of engineering discipline is here at SWIRI, and this is kind of the things. And this is kind of a sampling of a few of the things we do. And why I bring this up is who's using machine learning at SWIRI is literally everybody from deep space to deep sea and everybody in between. I don't think there's an engineering group here at SWIRI that is not either actively using machine learning or thinking about how it impacts their projects. So my group does a lot of computer vision and general machine learning. So we get to help out a lot of these other groups in what they do, as well as do our own projects. And it's just been a fascinating experience. Joining here in 2017, I kind of hit the beginning of the when convolutional neural networks were really taking off and people were really kind of going, yeah, these things are really going to change how we work. And then seeing how, just over the course of about 6 years, how that has progressed and changed in that short of a time period. And so the title of my talk was AI in the Wild. And there's this famous quote by Mark Andreessen from the early 2000s, and he said, software is eating the world. And now when you talk to people, they say machine learning is eating the world. And what he meant back then was everything was just turning into a software project. Everybody needed software engineers. Kind of all the engineering effort was shifting to software. And now we've just had this explosion of machine learning kind of taking over all these projects. And I've got a few samples here. You've got the Cruise self-driving car on the left there. In the middle is the Google Photos logo, which they heavily embed AI in. Google heavily embeds AI in everything these days. And then we're even seeing machine learning in things like medical diagnostics and prognostics, where we're using things like X-rays to look for pneumonia. COVID was definitely a boon for this. A lot of work that was done on detecting and diagnosing COVID patients used machine learning. And so it really feels like we've kind of just embedded machine learning everywhere in our lives. But everything is not awesome. These are some of the headlines I took from news articles that were about those projects I just had on the previous page. These are all pretty recent, actually. Just within the last month, GM's had to recall about 80 of their self-driving cars in San Francisco. The EFF noted that we've had some incidents of Google accidentally flagging photos as being illegal content. And then Andrew Ng, who led that study that produced that pneumonia picture in the previous slide, from that very same paper that he introduced that picture, he said, hey, this works great on test sets, but it's failing in the real world. And by failing, he meant it worked well when we trained it on this particular machine in Stanford. They trained it on a huge variety of demographics, people, everything they did, everything they could do to expand that data set. And when they went out down the street to the hospital down the road, it didn't work because they had a different machine and the technicians used slightly different procedures. And I also have this fun picture, I'm hoping this shows up over the web, of a paper called Wino Ground, which came from Facebook and Hugging Faces. And they were testing the ability of these kind of large language models like DALL-E and Stable Diffusion to understand the spatial context of their text prompts. So they said, show me a picture of some plants surrounding a light bulb. And you got this nice picture on the left of a light bulb somehow floating in a bunch of plants. And then they said, well, show me a light bulb surrounding some plants. And the generator then produced a light bulb containing a miniature terrarium full of plants. So we've still got a ways to go. And I think this is also interesting because you look at the resources that these companies have, Google, Facebook, Cruise. These are companies that are putting billions and billions of dollars into research into AI, and they still struggle. They've got amazing products. I'm not running down the engineers that are there. They do amazing things. But I think everybody in the industry kind of knows that there are still a lot of shortcomings. And if you have an organization with the kind of capabilities and resources of Google having problems, what hope do we have of smaller companies using this technology? Because that's what we see a lot here at SWIRI is people come to us when they need AI expertise, and frequently they're small, medium, even large businesses, and they just say this is beyond the scope of our capabilities. They certainly don't have billions of dollars to spend every year on their AI engineering and development, and they're struggling, and they may be in a niche market. So collecting self-driving car data is somewhat easy. If you're looking at some kind of niche manufacturing or medical problem, it's a lot harder. And so how do we kind of go from these huge projects to deploying AI in the real world? Well, this is kind of the spoiler slide. Um, what do? We have to understand our tools. We have to understand the limitations of those tools. And then really, we have to use our engineering knowledge to work around this and still manage to, even though we have limited, our machine learning models are limited in certain ways, we can still design effective engineering solutions to real world problems. And I think that comes down to, using not just what you learn in your machine learning course, but hopefully as students, you're developing a, very broad background and these fundamental engineering skills that I think really apply to this domain. And we need to keep those in mind as you go into the real world. And so that being said, I brought up a few case studies here. Some of them are more detailed than others, but I think they kind of highlighted some of the progression we've seen in machine learning and how we here at SWIRI develop these tools and deploy them. And I'd really like this to be more of a conversation. I don't like just giving straight lectures, so if you have questions, feel free to raise them in the chat, and I'm happy to address them as we go. So I've got 4 case studies here that kind of span these 3 areas. And the first 2 were commercial clients of ours, so I'm being a little intentionally vague on what we did. We have non-disclosure agreements with our clients, so I can't describe exactly what we did. So no matter what, I still wanted to kind of present the challenges that we encountered and present what kind of how we overcame them. So the first project we did, this was something that I worked on the first year I was here at SWIRI, and this is one of the first projects we really had that was like this like really great, almost pure machine learning application, which was how do you do this surface inspection of these industrial objects at a large scale? So this client had just this enormous number, spatially large area they needed to survey that was full of just, kind of complex objects. So think like these tanks here that I've put as illustrations. They've got, lots of curved surfaces. There's lots of, things on the tank. There's lots of valves. There's lots of hoses. There's lots of just challenging things to work with on these tanks. And they wanted to do a pretty standard industrial inspection, which was find things like, are the tanks cracking? Are they fatiguing and breaking? Are they discolored, which could indicate that there's something leaking or even lightning strikes? Are there, paint bubbles on the surface of these tanks, which could mean that they're starting to degrade and need to be repainted? And this is something we've actually seen a large number of industries want to do, anywhere from like highway inspection when they go and inspect bridges to things like wind turbine inspection. This is a pretty common task now in machine learning and the AI world, which is go out and just survey this huge industrial system that we previously couldn't, or reduce the kind of time it takes to do this inspection. And so this client in particular said, we want to use a UAV because we're trying to cover this big area, and we kind of need to work around this kind of site, so it needs to be maneuverable. And the UAV they thought made a lot of sense, and it does. So we were a little bit constrained there. And so we built this system for them, which was this Matrice M600. That's a good-sized hexcopter UAV. It can lift, like 5 kilograms, so it's pretty big. It's getting up to the upper range of what you can fly under Part 107 FAA rules. We put an Insenso stereo camera on it, which is a a pretty high-end industrial inspection camera that we borrowed from our colleagues over in our manufacturing robotics section. This is a very, very nice stereo camera. It has like a pattern generator that improves the 3D point cloud it produces. It's really nice. It has a range, but it has a range about 1.5 meters. And then in addition, we put this small Hikoyo LiDAR on it. And this was more for situational awareness to the pilot. It let them fly up very close to things. And when the LiDAR, and using those LiDAR returns, we could then say, hey, you're getting close to something, back off. Or you need to get closer to get in range of the stereo camera. This was a very practical consideration because if you're flying, 100 meters away from something, it's really hard to gauge how close your UAV is to it. So LiDAR just gave us situational awareness. And then on the software side, we really used Caffe. So like I said, this was, kind of 2017 era. Caffe and TensorFlow were kind of the machine learning frameworks in vogue at the time. And we were comfortable with Caffe, so we went with it. And then we used SolidWorks for some of the other engineering tasks on the project. And on the machine learning side, we kind of started off and we said, well, our plan is we're going to use these images that the client provides of existing damage that they've gone out and seen. They said they've got a bunch of images. We'll use that to start with. We'll kind of train this classifier to look for these types of damage they've indicated. And we'll use that to train this neural network. And, and as we do the project, we're going to collect more data. So we'll refine our model and make it even better. And we went with kind of a YOLO-like network to locate and classify damage. So YOLO is one of the things, if you want to, I'm guessing you're all familiar with YOLO, so I won't expand on YOLO. But the network was very similar to that. And so we basically went out to the client site, flew around this industrial area they wanted to inspect, collected a bunch of data, tried to train a classifier on it, and basically we failed miserably. And so this is where I wish I had pictures of what was going on. But what we found out was most of their system was actually in pretty good shape. We didn't actually find that many defects, and the defects were really, really small. So we were thinking when we went out there that these defects are going to be like, this enormous crack. And it turns out that they had like tiny, like nickel-sized damaged areas, which are a lot harder to detect. And you need to be very thorough when scanning the area. And because the defects are so rare, it's really, really hard to generate enough training data to detect them. If 1 out of 100, if there's 1,000 tanks out in their site and maybe 1 in 100 has damage, then you've got 10 tanks that are damaged. And how are you going to train a network off this really tiny data set? And that also leads me to their second point, which is computer scientists have this vague notion of working with big data. And depending on what domain you're in, big data means a lot of different things. And so as you move into the real world and start doing or do multidisciplinary research, you really find out that you have to speak the language of whoever you're working with. And so sometimes big data for, say, Google might mean a petabyte of images, 600 million images, whatever they use to train their networks with. Somebody dealing with like medical prognostics may say, well, this is a very rare disease and big data means data from a few dozen patients. And so when we were working with this client and we said, okay, can we have your training data? And they sent us a few dozen photos, and we kind of said, that's great, where's the rest of it? And they said, no, this is a lot of information. This is like a year's worth of defects that we found. And so we realized we should have been more specific from the get-go with what we mean by we need a lot of training data. And we also found out that, practically speaking, the sensing platform was very challenging to work with. The UAV would go out into the real world and get blown around by the wind. Sunlight would reflect off of surfaces, so you'd see just images with lots of reflections that were really challenging. And so everything was a lot harder than we thought it would be. And so we kind of stepped back and said, well, what do we need to do? And a couple of things.
David, there are a few questions.
Okay,
Maybe
sorry.
I would like to pause for a minute here. Can you read the chat questions to help read them to you?
I'm not sure I see chat right now, so.
I can read them.
Yeah.
I think the first question is from Sean. He's asking, how do you evaluate a project's fit for machine learning versus other computational methods or conventional experimentation approaches?
Yeah, so that is a great question. Right now, there is enormous pressure to make everything machine learning and AI. So I've had people come up to me and they said, my CEO said, we have to be cloud and AI forward. And sometimes you will get told to use machine learning and AI, but it's not always the right approach. And so I think there's a lot of value in understanding kind of classical computer vision algorithms. And sometimes you just look at a project and say, hey, I don't need machine learning to do this. I can do this with, a standard feature descriptor like SIFT or ORB or some of these kind of, non-deep learning based approaches. And I think it's going to work. And if that happens, I think it's great. It makes the project so much simpler because you're probably not having to detect as much data or collect as much data. So I guess step one is use your engineering knowledge and say, can I do this with anything other than machine learning? Step two is you kind of look at how hard it is to collect this information. If it's something that we need thousands of hours of footage of something, of like if you want to collect thousands of hours of say video on a factory line or something like that, you have to assess whether that is realistic with the other project constraints. If they say, if you kind of think, well, I need 1,000 hours of video and we need this done in 3 weeks, you're not going to get. It doesn't matter what you do, you're not going to get 1,000 hours of video that fast. And then, some of it is you have to be realistic about the expectations of how well it's going to perform too. If you need something that has, if you're dealing with like a safety critical system where it is absolutely vital that it not fail, you have to be realistic about what you're going to get from the machine learning platform. The best neural networks, thinking about even trivial examples like the MNIST data sets or something like that, or COCO or any of these open source benchmarks, and the best neural networks may, be, even a very, very good one may be going at like 97% accuracy. Well, 97% is phenomenal and great in some cases, and in other cases, it's really not acceptable. For example, if I'm building a movie recommendation algorithm for some video streaming site, and 97 out of 100 of my recommendations are really good, that's great. And if I recommend you 3 bad movies that you don't like, there's really no downside to that. But on the other hand, if I'm building an autonomous car and it detects 97 out of 100 cars and surrounding traffic accurately and fails, 3% of the time, the consequences are much more severe. So,
I think those are great points, David. I think as a follow-on to that, I'll skip some of the questions here to add to this point you just made. There was another question asking if in real life situation, there is often a lot of noise in the data. How can the models be equipped to counter noise and statistical variations in real life data compared to training data?
Wow, you have some great students. I think we can just skip to the end of the talk and we can just have a conversation. Yeah, so there's one school of thought, which is augmentations. Definitely always augment your data. A lot of times that's challenging to create realistic augmentations. It's pretty easy to come up with some kind of, the standard augmentations, like I'm going to warp and scale and skew my image, my input image. Those are pretty common. They do help performance quite a bit. But when it comes, I think the really hard thing is where you have these kind of outliers in the data itself. When something, and I'll talk about this in the next kind of case study, but when it's not so much noise as it's just something unusual that came down the line. I don't want to bag on Tesla, but if you look at some of the issues Tesla's had, or general self-driving cars with things like the other week there was an incident in Pennsylvania, I believe, where somebody was using their level 2 self-driving car and they drove into a horse and buggy that was going down the road. And you think about that, the horse and buggy isn't really noise, it's just something very unusual in your training data. So making a large enough training set helps with that, but you're always going to have weird things. And that's where I think you need to step back and from more of a systems design standpoint, be aware that there are always going to be things that don't appear in your training data set and come up with ways of saying like, hey, this looks like nothing I've seen. I need to alert an operator, or I need some other mitigation method outside of my machine learning framework to deal with this.
So I think you just touched upon it, and I see that you also have this on your slide, but there are two related questions on the same point in some ways about augmenting your data, right?
Yeah.
So, I think one question was related to saying if there are unbalanced data sets like similar to what you have, it often happens in medical domains. Aaron was pointing to this, and do you pull data from other domains to solve these type of problems? And how do you kind of do this augmentation in general to increase your training set size?
Okay, so there are kind of three questions there. So I think the question about pulling from other domains, that's great. I think we did, and I think the slide that I talked about, that I was going to talk about here, kind of hits that. Yeah, you can use surrogate data. So we were looking for defects in this industrial setting. So we went out and found somebody's hail damaged car and just scanned that, because that's also something we were looking for. Bringing in other domains is absolutely possible and a good idea. You have to be, sometimes it's hard to do that in practice because you may have either confidentiality requirements or licensing restrictions on the data you can use, especially if you're looking at medical studies. The data you collect from one medical study may not just be easily transferred to another one because of privacy concerns. Augmenting the data, there's simple ways of augmenting the data, like I said, like skewing it, rotating it, flipping it, all, color adjustment. And those are usually, and those are almost always part of our process. Like, it's just a best practice that I think everybody should, had better be doing. as part of their training process. I do think the more challenging thing is when the augmentations are no longer a simple kind of manipulation of the image. And I think that's where we'll frequently also turn to synthetic data. So, and that can also help kind of rebalance the data set as well. I think that was the first question about class imbalance in your data set. There's, common ways of fixing that is like, reweighting the weights so that you penalize it for missing the rare classes more heavily. But you can also use synthetic data and try and artificially boost these kind of rare classes, which I think is a really valuable tool. Training autonomous cars in synthetic environments is great. It's really powerful. But again, there's limitations to it. If you want to simulate medical studies, it can be really hard to generate synthetic data for that, and you probably need somebody who's an expert in the field to do it and work closely with them. So you don't want to generate nonsensical data. So frequently it also comes down to working closely with whoever you are partnered with to really do it. Machine learning is a tool. It's another tool in our engineering toolbox at this point, and you need to be able to communicate with whoever you are working with to really accomplish their end goal.
So our students and faculty are on a roll here. There are lots of questions, but I guess I'll let you finish your talk quickly. Maybe then we can go back to these questions. There's a lot of curiosity here.
Yeah. So I'll just kind of, the highlights of this is what we ended up really solving this problem with was, after we tried, using a bunch of surrogate data, we just realized that it is almost impossible to simulate all the damage that can occur to these things in real life. And after an enormous effort in trying to augment the data, find other examples of damaged surfaces, it still wasn't working well enough. And so we ended up actually switching our entire neural network architecture from kind of that YOLO system to an autoencoder. And if you haven't used autoencoders, one way of looking at them is they're compressing down the image. And at some point in that compression, you can kind of say, well, what stands out in this image? Like, what is not part of my training set, or was not compressing well, which means I haven't seen it before. And so it really helped flag irregularities in the data. So that helped us find, like, okay, there's some dent in the surface of this. I didn't really train on a particular shape or anything, but it just looks so much different from this like general curve that it's on that I can flag that and have an operator go take a closer look at it. And this mostly solved the problem, but we also found that there are many things in the wild that look weird but are expected, like stickers on the tank and things like that. And so kind of the follow-up work to this, or not follow-up work, but we had a closely related project, and now I'm finding my cursor again, which was another industrial automation project. And in this case, it was more of a it is a factory setting. And so you can kind of imagine a traditional factory with robot arms, and it looks like this, where the robot arms kind of do the same thing every time. They perform the same operation again and again and again. They put the car on the same make and model of the car, or they put a door on the same make and model of the car. They do that with high repeatability. They work really well, but the factories of the future, or that we're currently helping build, we're dealing with a lot more dynamic environments. So we're trying to do things like build multiple car types on one production line. So the robots have to understand what they're building better, so that they may have like a hybrid vehicle powertrain and a electric vehicle powertrain on the same production line, and they need to like dynamically shift which parts they're doing. We're also dealing with a lot of things like sanding and rework on parts. So there may be a problem with a part, and we're going to just throw that on this conveyor belt, and some robot arm is going to figure out what it needs to do to fix it. And this particular client had something like that. They had a highly dynamic part mix that had huge differences in scale of the pieces they were manipulating, and it had huge differences in appearance. And they had, what they were working with was a laser line scanner, a industrial rework tool, and this fairly complete industrial system, PLC for safety, an operator, and a conveyor line. This was once again a 2017 era project with CAFE. And we really took a lot of things we learned from that earlier industrial inspection project and applied it to here. And so right from the get-go, we really worked with their subject matter experts to better label the data, make sure that our data set reflected what we were going to see in the real world. And we also worked with them to modify the machine to optimize kind of the sensor configuration so that we would get the data we needed to make it work the best we could. We also collected problem images in the factory to augment our initial data sets. So a big part of it was when we started collecting data, we just put a button on the human machine interface where the factory worker could be like, hey, this looks a little weird. I'm going to collect this image to send back to my supervisor, and we can augment the data set that way. And that goes back to the class imbalance problem where instead of just collecting, thousands or tens of thousands of kind of these good images that we were working well on, we really started focusing on the problems with the pieces and products that had kind of weird things going on. And we trained the semantic segmentation network to classify the pieces of the image. And so what happened was we kind of did all that, and actually we got a pretty good network going here at SWRI. It was probably performing better than 90% success rates. And the client was pretty happy because they had been trying to use conventional computer vision and failing at this, because this was a case where conventional computer vision just couldn't cope with the enormous variety of appearances that were going through the machine. And we really said the network was good, but not good enough. So what we did was we really had we almost put this into production, and we just said, like, hey, all these plant operations people, give us data every time it fails. And then critically, a lot of the things we fixed weren't with the network itself, but we said, hey, why do these things look weird? And we went to the plant operations people and we showed them it, and they said, oh, that's actually because we had some other problem in our process. We can go fix our process and give you the data and make the thing work like you need it to work before it gets to your system. And this system is actually in production now, which is pretty exciting. Like I said, SWRI doesn't do a whole lot of production systems. This is one of them, however. And kind of going from like good to really a production system is we have, in addition to all the network, we had to do a lot of things like work with their subject matter experts to know when that network gave us good data. So they had a whole bunch of like common sense based things based on the physics of the product, where they said, hey, it doesn't, if your tooling path is going to encompass 40% of the product, it just doesn't make sense. Like, you're never going to rework that much of the product. It means something else is broken. So we basically took their kind of like domain knowledge and made a bunch of rules for the system so that when after the neural network operated, we went back and said, hey, does this conform to what the subject matter experts say it should do? And if it doesn't work, then we're not going to try and do something to it to damage it. We're not going to move a sander in here and just completely wreck this system. We also implemented a lot of conventional path planning procedures for the tooling. A lot of people want to just go straight from machine learning framework to a path plan for the tool, but instead we stepped back and said, no, we can, kind of use some conventional techniques that end up working just as well and don't have these kind of hard to explain behaviors. We also found out that just the HMI, the human machine interface for the production line workers, ended up being a huge deal. This has nothing at all to do with the neural network, but has everything to do with how well the system works for the end user. We implemented just huge changes for them so that they could see what's going on, and it gave them the confidence to accept the machine, which is sometimes a very big deal. They don't just want a black box, because anytime it fails, they're just going to be like, this thing is crap, and they'll just reject it. And it turns out that you can't really control what those production line workers do in a lot of cases. And if they think it's not working right, they're just not going to use it. And we also learned a lot of things about deploying production machine learning frameworks in terms of how long they will last. As I said, we started off in Cafe, and I'm guessing a good chunk of the people on this call have never actually used Cafe at this point. This is a big problem when it comes to kind of moving these neural networks out to the edge and into areas where they can't easily be updated. If you do, if you're doing like web platforms where everything's processed in AWS, you can kind of transparently switch out your machine learning framework, and the end user never knows. When it comes to deployed machines in a factory, they want them to rarely be updated. And so figuring out how to, and so some of the things we learned were we needed to use tools like ONNX or Onyx to put our models in a common framework, so that way we can better swap out machine learning frameworks as we need to. Currently, we've switched to like PyTorch with this software just because Cafe is no longer supported. So the kind of churn and rapid development in machine learning is really exciting. When it comes to production machines, people are less excited about having their machine learning framework swapped out from them constantly. And I'm actually coming up on 1140, so I'm going to skip this one. We did some non-human primate tracking with Texas Biomed, which is our sister research organization. I wanted to throw in this fun slide of my master's research where we were working with cranes to track them. We have a lot of exciting human performance software that we've once again worked heavily with our biomechanics group here to develop, and again, incorporate the biomechanics experts' knowledge of how the human body works, so that when you do these kind of joint tracking tools, you come up with something that is actually kinematically feasible for a human body to do. And then we ended up deploying this type of network out to Texas Biomed to track some of their baboons.
Motion capture technology uses.
And it was a fun project. I'd love, if anybody wants to talk to me about it, I can talk a lot about it. We ended up doing a lot of really exciting things with working with fairly wild animals and their cages. But I'll skip that in favor of going on to this last case study, which is at this point more speculative. This is our space robotics program area, which we just started up. So this is kind of a new area for SWIRI. We have a deep heritage in spacecraft systems. We've been on over 50 NASA missions at this point. And we kind of said, we've got all this expertise in space science. We have all these robotics experts, all these computer vision experts, all these AI experts. Let's do something with this. And it's a really great time for it. I'm excited about it because the space industry is rapidly evolving. We're seeing this kind of change from very kind of statically designed missions where the spacecraft does like the exact same thing every time, because spacecraft are incredibly expensive and no one likes seeing their satellite blow up, to much more dynamic things happening in space. And by dynamic, I mean the missions are less structured. It's spacecraft reacting to what's going on with them instead of just performing kind of open loop set of steps. And I think SWIRI is going to do very well in here. This is an OSAM mission from NASA. This is their illustration of it. And this is kind of the view of the future, where you can see we've got this spacecraft that's like unfolding, and fun news is it's now got a robot arm on it. And so this robot arm is actually going to go up there and do things to other objects in space, other spacecraft, other satellites, whatever it may be. And this opens up a world of doing things like in-orbit servicing, assembly and maintenance, or OSAM. So we can go up there, and if satellite is damaged, we can actually go up and fix a satellite in orbit. Whereas in the past, we would either put it into a parking orbit or deorbit it entirely. We can actually go upstairs up to space and fix things, but this is going to require a lot of complex computer vision and AI. Also do things like satellite refueling, geostationary satellites, and in fact, all satellites eventually run out of fuel. And when that happens, your satellite's done. Eventually, it stops maintaining its orientation, and your, $100 million billion satellite is just junk. So the idea is eventually we can go up there and actually just refuel the satellite and extend its lifetime, and doing things like debris removal. So things that are hard in space, and I saw I had some questions. I'll talk about that. Just give me like another couple minutes. Some of the challenges in space, computer vision is the lighting is really, really harsh, and it rapidly changes. If you're on a satellite, it may be orbiting the Earth every 90 minutes. So you're going from pure bright sunlight to complete darkness very, very fast. You also have to deal with fun things like radiation. Sometimes it can look like you're flying through a snowstorm up there. You have severe hardware constraints. When they talk about these kind of CubeSats, they want computer vision systems that consume on the order of like less than 10 watts and ideally less than 5 watts. So it's in some cases less power than your cell phone is using. And you're dealing with, frankly, hardware that is quite old compared to what you're used to dealing with here on Earth. Radiation tolerant components are just, sometimes it feels like you're going back a decade or more. We're not flying the latest NVIDIA RTX 3090 in space. I can guarantee you that. It's probably an FPGA that was old when I was an undergrad. So how do you take these kind of modern computer vision and machine learning techniques and kind of go back and say, what can we actually do on this limited hardware? Training data is enormously hard to get. Where do you get pictures of satellites that were taken from other satellites? I suspect that there's several world governments that have them, but they are not forthcoming with them. So where do you get that data? And then just the enormous variety of things that are up there. If you're talking about going up and getting orbital debris, that could be anything from like a used launch booster that's the size of a bus to, a bolt that the satellites dropped off of the ISS that's, the size of my finger. And so some of the things we're looking at here real quick, hardware-wise, there are now space-rated FPGAs, so we're looking at moving our machine learning to these FPGAs, but that's requiring us to really simplify the networks, limit the number of tasks we're asking the network to perform. So rather than having a general machine learning framework that can do the visual analysis at all ranges from the satellite, which could be hundreds of kilometers up to a meter away, break it into a series of smaller networks that operate at different ranges. Using simulated data. Over here on the right, I have images from the European Space Agency, which released this huge data set. It's the Satellite Pose Estimation Challenge, where they use physical mock-ups as well as purely synthetic data. And I want to put this in here just because if you can see closely on that upper right, you can actually see a bunch of icon markers on this physical mock-up. And if you're going to use the physical mockup, you need to make sure it looks like the real world thing. All the machine learning approaches I saw to this pose estimation challenge clued in heavily on those Vicon markers. Turns out that those are great visual fiducials for tracking the pose of the satellite. And kind of in general, also using different sensors. Do we need thermal sensors? Do we need neuromorphic cameras? Things that may operate better in space that we don't commonly or much less commonly used here on Earth. And so my takeaways are, if I wanted to give advice to somebody, don't treat machine learning as this magic black box. You're a trained engineer coming out of the university. You should use all these engineering skills you've developed, not just your ability to make a machine learning model to successfully execute on a project. Understand your tools. Don't just expect to throw models and data at a problem until you beat it in a submission and get good results. Be able to really read the research papers behind the machine learning models underneath and really understand what they're giving you, and don't just try and throw a model at it until it works. Take the best parts of one network and apply it to another, depending on your goals to achieve them. And consider machine learning models just one component in your system. Like I said, in the factory automation example, a lot of what we did was actually go back to their other processes and improve them so that our machine learning powered robot would actually work. Never underestimate how hard it is going to be to collect data. It is just tremendously hard. When it comes to collecting the data and labeling the data, really think about how much time you're going to spend on that. If you want to do semantic segmentation on a 10,000 image training set and you want to label it all from scratch, it's going to take a lot of time to get that data and also label it. And also really work with domain experts to understand what they're trying to use this machine learning framework for and use their knowledge. I can't emphasize this enough, that the ability to communicate with other disciplines to explain what you're going to do and understand their needs and incorporate their knowledge is just unbelievably valuable. And I think that, and best engineers I know are really good at this. A few other problems I didn't mention, that I didn't even get to in this talk: adversarial attacks on networks, biases in data sets and models. Who owns the data? That's becoming a big question with like these large Dolly and stable diffusion type networks. If you scrape the web and you incorporate somebody's unique art piece in your data set, do they get a chunk of your network that you derived from that data? And then broader kind of societal implications like deepfakes are everywhere. The ethics of using this. Some people are find that there are extreme ethical challenges in some of the areas that people want to use machine learning for. So just really need to be cognizant of all of this. But I don't want to end on a down note. There are reasons for hope. We're getting enormous amounts of tooling around machine learning frameworks that are so much better. It's so much easier now to do this and get feedback on how the network is training and diagnosing problems with it. We're seeing lots of high quality machine learning models and data sets get out in the real world, which is hugely valuable because you can use transfer learning on these data sets and models to, go from like a Google sized company to applying their data set to something that you can use on your small company. Really, engineers are getting very proficient with machine learning in general. They're coming out of the universities with better understandings of the limitations and benefits of it. And that also comes with realistic expectations of machine learning. It's no longer, when I started on this in the 2016, 2017 era, it was like every other startup was this: we're going to use machine learning for this task and it's going to be amazing. And very few of them panned out. I'd also like to point out that I have a huge number of collaborators here at SWRI that are just an absolute joy to work with. I really do appreciate all their insights and hard work they put into these projects. And with that, do we have questions?
Thank you, David. That's a powerful message that it is really important to explore the domain expertise people have and also the skills that you bring in from your fundamental training in the field in order to build better AI systems. So I think we have 5 minutes for Q&A, but David, if you're available, we can extend the discussion by a few more minutes.
Yep, I'm happy to stick around.
Okay, thank you. So just going back to your earlier case one, I believe there were a couple of questions in there from Panos. Panos, do you want to ask the question?
Yeah, certainly. hope you can see me. So, David, thank you very much. This was a great presentation and very, very valuable insights from the practice of machine learning. I could not agree more with your summary at the end. Indeed, you have, in many cases, we choose the machine learning algorithm to use just based on the application, but you have to take into account what data you have and customize your method to fit also your data, whether they're noisy, whether they're highly imbalanced, etc. So your method is very powerful indeed. Just a quick question I had on the first case study that you showed. It looks to me like an anomaly detection problem. And I want to ask if you tried things like maybe one class classification, if you found any benefits there. And the follow-up question on the same problem, did you try any methods for reducing the noise or the high variance in your data, maybe in the way that pictures were taken, or targeting specific features, looking for manually, with some expert advice?
Yeah. Yeah, so in terms of networks we used, I will admit I, I, I wish we had time to explore more of it. It kind of got down to the practical standpoint of, we had a finite timeline on the problem. Yeah, I definitely think we could have sat there and somebody could have written another master's thesis on this and just tried various networks for a year to see what worked best. Yeah, but yeah, we definitely ended up on the autoencoder just because of the huge range of problems we were seeing. And also, when it came to collecting the data, I think to your second point, we did try our image augmentations probably went a lot more extreme than we normally do, to the point of like, kind of trying to fake blowing out the lighting conditions in the image, adjusting the contrast that high to try and really obscure features in the image, doing a lot of, anything we could do to kind of fix, augment the data to look at like what we're getting out in the real world. We also did a lot of work to kind of improve the sensor configuration on the UAV to also eliminate those, try and eliminate like glare as much as possible, things like that. Boy, totally random aside here. If you ever want to do agricultural work, you'll find out that there are all sorts of kind of like unwritten rules about how to collect data in the agricultural world. So like only fly between the hours of 10 and 2 so that your sunlight is like predictable and it's like interacting with the plant's diurnal cycle in the right way. Yeah. But anyway, yeah, we did do a lot on the data collection side too to try and eliminate problems.
All right, thank you very much.
Thank you. Caitlin, do you want to ask your question? Okay. How about Chris York?
Hello. I guess it's an ethical question in reference to autonomous driving. If autonomous vehicles are only, say, one order of magnitude better than humans, shouldn't we push it or make it available or recommended to the public? There's hundreds of human crashes every day and you don't hear anything about it. But that one autonomous driving catches all the news. But it seems like when they're a certain level better than humans, it should be pushed. I don't really know if that's a question or a statement or if you'd just like to comment on it.
Well, we frequently have that discussion in the lab. And I see some of my coworkers are here on it, so we could probably sit here and recreate that discussion as right now. Yeah, the question of safety and do you just say this is better than a human, statistically speaking, let's deploy it. I'll say, first of all, I don't think we are there yet in terms of safety. There's lots of ways to spin the statistics in terms of what is safe. The reality is and I think this also goes to the kind of sociological and psychological aspects of the problem too. So many of the car crashes right now are due to things like bad weather, impaired or drunk driving, people just doing, people doing stupid things, in the car, exceeding the speed limit. And so I think kind of from a psychological perspective, when we're weighting kind of the risk and reward of these autonomous driving systems, everybody thinks they're a great driver. And in a way, it's kind of hard to say, like, is this safer than what I drive at? And I think just psychologically, there's kind of a barrier there to adopting them, because it's easy to say, like, well, most of the car crashes are because somebody did something they shouldn't do, they violated the law in some way, and I don't do that, so I'm not, self-driving cars don't make me safer. I think also the challenge there too is kind of related to that when it comes to assessing the safety of them. Even if it was, let's just say we get to the point in self-driving cars where it is just statistically safer, right? Like it is, the cars are better than, if there are 60,000 traffic deaths in the US a year, we can say, like, yeah, we're going to reduce that number to 55,000 just by making everybody have a self-driving car. The question still becomes, is the behavior explainable and safe enough that people aren't scared of that self-driving car, right? Because if I'm, oh gosh, now I'm really going to go down a rabbit hole. I think measuring the safety is hard, and there's other barriers that are not just technological to adopting them when it comes to safety. Maybe I'll cap the discussion there.
Yeah, I think, thank you, David. There is kind of a related question, not necessarily ethics, but Jeremy has this question. Jeremy, do you want to ask?
Sure. Kind of a follow-on to that, loosely, let's say, as these technologies are starting to deploy in the commercial and industrial environments, what kind of explainable AI do your systems use, both in the realm of gaining customer trust and also for continued development on your systems?
Yeah. Oh boy. Explainable AI. That would make a great that would make a great topic for one of these talks. It's challenging because at the end of the day, really people care about whether it works or not. And some of the tools we have for, say, going back through layer by layer and looking at where it kind of blew up in the model itself. It's great when you're debugging and developing the network, and the end user probably does not care about it at all. When you go convolutional layer free and the backbone had some singularity and exploded, it doesn't really, it's useful to fix it, but it's not really useful for the end user. So some of the things I've done is try and make nice UIs for it that kind of say, like, try to explain, like, I misdiagnosed this, or this is how I diagnosed it. And so at least they can kind of look at it and try and get some idea of where it went wrong. We did a lot of work with the factory automation to kind of give them a bunch of knobs to turn, so to speak, that they could kind of fine tune and adjust it. And some of those adjustments happened outside of the neural network. Some of it was just like, some of the things they found out was just like, oh, the machine is just biased one way. Like, it's always a millimeter off. And sometimes it's just a matter of giving them a knob to just manually adjust that path back to that, like, correct position. I think where it gets interesting is in, like, the medical field. There was a great paper in the Lancet last fall now, looking at, like, x-rays, and they just sat there and said, like, hey, we can actually use this training set as, like, a way to actually classify or detect people's, like, I believe it was their race. And they sat there and they just did a ton of ablation studies and said, what features in this are causing this behavior? And sometimes you need to just do that. And maybe that's another tool you can use, is just kind of an ablation study, or to sit there and augment it with noise and figure out where it's failing and kind of say like, hey, just be able to summarize to the end user that like, hey, it's not going to work if you're, you know, more than like 30 degrees off axis of the camera, or you just need to characterize the network performance. If it's a car detector network, say the car must be at least 20 pixels by 20 pixels in the image or we aren't going to detect it. And just giving them some limit rather than just being like, oh, the car gets tiny and it goes away in my neural network model. Really thoroughly characterizing it and just giving reasonable explanations as to when it fails and when it doesn't. I wish I had a silver bullet for that. It's definitely a challenging topic and just interesting in general.
Yeah, I think that's a grand problem in the field. We're all trying to work on it or think about it. So there are no easy answers. There are a few more questions. Excuse me. Sergio, do you want to ask your question? Well, I don't see Sergio. So perhaps we can move to Garrett Hall. But I saw Garrett. I can ask Garrett's question. He's from Southwest Research Institute. He's asking, do you think the deep learning or machine learning will be able to generate the code the way Midjourney? I think the more recent example on the stable diffusion images that we've seen, do you think machine learning will be able to generate code that is able to generate images based on text?
I'm not sure I understand. I'm not sure I understand the first half, but yeah, I mean, we're able to generate images from text, but what's the?
I think that question is more if the model itself can generate the code.
Oh, code based on text. Oh, okay, I see. So like, it's the please make my computer do X and it generates a program to do. Oh boy, that excite. I personally love that question. I had a bunch of colleagues in grad school that are now professors that are looking at what they call end user programming. If you're in software engineering, I believe that's the right term for this. And it's kind of this general idea of, yeah, like how do you have somebody who doesn't know programming develop these like really advanced programs, like, you know, the magical Excel sheet that all businesses run on that have like tons of Excel macros that, you know, somebody hacked together and make work. You know, I will we get there? I think I think the immediate path on that is being able to do things like not only describe the code you want, but also be able to describe the test cases. I think would be able to help in that regard. You know, because in some way, if I had a complete set of unit tests for a chunk of code, that might help my machine learning model know whether it's working or not, right? Like it can know whether it generated code that satisfied the problem. So I think part of the problem, and so I think that's related to when we talk to the computer, we use very non-precise language. And so if you could describe your problem very mathematically, yeah, I think we will get there. But I think we will get there. I think the challenge is going from these more informal descriptions we have of problems, and that is a wild problem. Wildly hard. I think it's interesting. I think it's just, you know, yeah, eventually we'll, you know, if I say we'll never get there, you know, somebody will come out with a paper in a year that's like, hey, I solved this problem. I think it's an incredibly challenging problem. It's probably ways off in the future.
Very well said. So there are two more questions. One is from Sergio. He's not able to read it. I'll read it for him. Are you using reinforcement learning techniques for some of the examples you've shown in the space robots?
Yes. We have used reinforcement learning in our manufacturing and robotics division in the past to solve, problems that, to solve like robotic arm problems. I don't think we've pushed it quite to the space robotics side yet, just because some of the kind of tooling around it is not where we are. Hilariously, as an aside, one of the problems we have with kind of all of our space, putting an arm into space, is now you're in zero gravity. So you have to think about conservation of momentum. So if your arm reaches out in space, that means your base is pushing back in the opposite direction with the same momentum. And doing that, which is opposite if you're on Earth, where generally we assume that the base of a robot arm is completely fixed in place. So eventually we will probably do reinforcement learning on it. We just have to update a lot of the tools we use to work in space and then get them plugged into the machine learning pipeline so that we can do all the reinforcement learning we want.
Great. The last question from Nitish. Do you want to ask the question?
Hi. So, how challenging is it when you're simulating this robot data, and how you approach this from ML or AI perspective?
Yeah, so the good news is the simulation tools available to us now are really much better than they used to be. Not only in terms of quality of data they have, but also the accessibility they need. Like around 2018, I think David Chambers, one of my colleagues, is on this call. We had a project from a commercial car company that we use simulation data for, and we basically needed to simulate a whole bunch of trailers. Actually, like they wanted to like back up into a trailer and automate that process. And we used Unreal in that case to generate lots and lots of fake trailer data under different lighting conditions, because we can't physically buy enough trailers to simulate that. So in that case, it was a fairly straightforward process. The more common the scene is, the easier it is to simulate, because somebody's probably already generated like all the models you need and things like that. It's when you start talking about like space or these other kind of harder, less common applications that some of the challenges is just generating like all the 3D assets you need to correctly model that environment is really challenging, or I shouldn't say challenging, time consuming is the right word. Time consuming. It's easy to cut corners in that process and get kind of crappy simulated environments. Like if you're trying to simulate a forest environment, you don't just want to plop the same tree model out there 10,000 times, because your neural network will learn to classify that one tree model very well. So back to my original point. Yeah, the tooling is getting a lot better. Sometimes the troubles are just generating the 3D assets that go into it, but it's becoming an increasingly large part of our just normal everyday workflow. Rather than being kind of this like exceptional step we had to take to really go out and generate a synthetic data model, it's not every project, but it's rapidly becoming something that we use very commonly, just as part of it. It's becoming another tool in our toolkit rather than some exceptional thing we have to go out and really spend a lot of effort doing. I don't know if that answered your question very well.
Yeah, thanks.
David, sorry, there was one last question that I missed. This might be quick to answer. Kevin, do you want to ask?
Yeah, thank you, David. Thank you for your presentation. So I find you use the LiDAR and the camera in the project. So I would like to know whether you fuse the LiDAR data and the camera data together, and if yes, how do you fuse these two kinds of different data together? Thank you.
Yeah, that's a great question. Data fusion. For the UAV inspection one, we didn't fuse the data because the LiDAR we had on it didn't have the spatial density of the point cloud. The spatial density of the point cloud it produced wasn't high enough to really be useful in this application. Recently, though, Logan Elliott, one of my works next to me, he's been wrapping up an internal research project that actually does fuse camera and LiDAR data for mapping applications. And so how you do that fusion, once again, depends on what your end goal of the project is. If you're looking to build a better classifier, you're going to do one, you might, kind of feed both sets of data into the network at the same time, have kind of like one big network. This mapping project that we're wrapping up, I think is really interesting because it's using classification from the camera to basically heal the LiDAR maps. So when you have a obstruction in your way, you can actually remove that obstruction and intelligently infill where that object was to produce a better map. It's like if I drive through a parking lot, there's a bunch of cars parked in the parking lot, and I want to remove those cars from my map to make it more correct. We can fuse that LiDAR and camera data to produce a better map. I think sensor fusion is incredibly interesting. I think that's another interesting topic that is enormously valuable to the commercial industry. And it's challenging not just because from the network standpoint, but also again, how do you collect that data? It gets to be a really fun problem. We've also looked at doing things like trying to simulate thermal data from visual imagery. So predict like where the hot spots are going to be on a car based off of its visual appearance, things like that. I think it's a really fascinating area. If you're interested in researching it, I think it's a great topic.
Okay.
Thank you.
Thank you, David. That concludes the questions from our end. I think this is the longest ever seminar session we've had in the Matrix. So that shows how curious all our researchers are about this work and the challenges of deploying machine learning in the wild. Thank you so much for such an insightful talk and a great discussion. And if some of you have further questions, I think you might be able to reach out to David.
Yeah.
Directly. And that's all for today's session. Thank you all for joining us and have a great weekend. Bye.
Thank you, everyone.